Is lecture number 5 in a introductory course in electricity and magnetism. And in this lecture, I'm going to introduce a new concept called the electric field. And I've got two learning outcomes. One of them is, so the electric field is a vector, and I would like you to learn how to approximate the direction of an electric field somewhere due to a point charge or a collection of point charges. And this is very conceptual. The other learning outcome is to learn how to calculate the net electric field vector somewhere due to a collection of point charges. And as I read this to you, honestly, I wish it was in the reverse order. So I'm going to delete that one and add it instead to here. Yeah. So in order to show you how to perform these kinds of tasks, I'm going to start off by describing or defining the electric field of a point charge. And then after that, so this is the electric field of one or a single charge. So of a single point charge. After that, using this actually, I'm going to show you how to combine up the total or net electric field of a system of multiple point charges. There is a really big idea. It's called the superposition principle. And I'm going to introduce you to this idea and how it works. But you'll see that all this is the superposition principle. It's simply the vector summation. Yeah, and honestly, this is kind of a big deal. This is how you're always going to combine electric fields. So you're going to learn the superposition principle in this lecture, say, but you're going to continue to use it all the way through the course. Every time you think of electric field, you should automatically assume that you may have to combine electric fields according to this thing called the superposition principle. And when we work on the net electric field of a system of point charges, we're going to do a very particular charge distribution called the electric dipole, as an example. So in order to introduce you to this new concept of the electric field, I'm going to simply define the electric field of a point charge at a place called P. So P is a coordinate. Another word for coordinate is a location. And so P in three-dimensional space is a place in a coordinate system, and we could say that it's given by a position or a coordinate xyz in some coordinate system. So the idea is I have a point charge, and I'm going to show you how to calculate the electric field of a point charge whose charge is Q. So I'm just going to define it. That is, I'm going to give you an equation. So the equation looks like this. So the electric field of Q at P, it's equal to 1 over 4 pi epsilon naught. So this looks a lot like the preamble to Coulomb's law. You multiply by the charge Q, whose electric field we are studying. You divide by the distance between Q and the place P squared. And you multiply by the unit vector r hat that points you from Q to the place P. So place P is a position. There is not necessarily any charge at P, but there is field at P, but there is electric field at P, and this is how you calculate it. This is the electric field at P. Really quickly, if you were to study the physical dimensions of the electric field, that is, what units does it carry, it turns out that the SI units of electric field are newtons per coulomb. So the physical dimensions of E are force per charge. So that's the physical dimensions of what I'm showing you how to calculate this electric field. So epsilon naught's got some crazy units. Charge Q has units in SI units, it's the coulomb. Here's meters squared, and of course the unit vector doesn't have any units. But the units in the rest of this formula amount up in the SI form to newtons per coulomb. Force per charge is the physical dimension of the electric field. So far I've only just defined this thing for you. So really quickly, there is a vector, right, that I'm alluding to, a lot like I alluded to vectors like this in Coulomb's law. This equals means is. So R sub QP is the vector from Q to place P. And I'll insert right here, it's from the charge, the point charge Q, to the location P, where P is some place in space. So let's have an example. So let's imagine I have a coordinate system. So this axis here is the z-axis. It sort of points out towards you. This is the up-down direction, the y. And this thing right here is the x direction. And you use I hat to move in the x direction. You use j hat to move in the y direction. And you use k hat to move in the z direction. So this is how you move around in the space. And I'm going to put the charge capital Q here at location. So let's say a distance A away from the origin of this coordinate system. So the origin is at the crossing of the three axes. So in this example, Q is at the coordinate 0, 0, A, right? So A is some distance. It's the distance that the charge Q is away from the origin along the z-axis. Okay? And I'm going to ask, what is the electric field that belongs to capital Q at the location or place called P, if P is the coordinate, say, I'll say a distance d along the x-axis, 0, 0, right? So a distance d along the x-axis, I don't know if d is bigger than or smaller than a, it doesn't matter, so I'm just going to put it somewhere. And I'm going to assume that d is positive and a is positive, so I've gone out the positive z-axis and out the positive x-axis for P. Okay, so this is my example problem. So let's try to fill in some details. So I'm going to use this definition of the electric field at place P due to the charge Q. So what I need to do is, so the electric field that is because of Q at P is, remember the definition is 1 over 4 pi epsilon naught. It's the charge Q itself divided by the distance between the place where Q lives and the place where we want to know the electric field at. We need to square that distance, and then we multiply by the unit vector that points from the place where Q lives to the place where we want to know the electric field. So here is the definition. This is just the definition. So let's fill in some values. 1 over 4 pi epsilon naught, we don't have any choice about. They're fixed values. The charge Q, we are interested in the electric field due to capital Q. But R sub QP squared, right? So this is a distance squared. And it's the distance between the charge Q and the location P where I want to know the electric field. And that distance, can you see, it's sort of the hypotenuse of the distance D along the x-axis out to P, and the distance A along the z-axis out to the capital Q. So the distance between Q and the place P is that Pythagorean distance. So it is a squared plus d squared. I hope you can see that. So that's just filling in the Pythagorean theorem, hypotenuse squared. But r hat sub qp is a little bit more difficult. So I need to figure out what is the unit vector that points from Q to P. So the unit vector I'm talking about points from Q over to P. I need to figure out how to construct that unit vector from Q to P. So here's how I'm going to do it. I know that what this vector needs to do is go backwards in z by a and forwards in x by d. So the vector, the full vector, not the unit vector, but the vector that points from Q to P, what it does is it goes backwards by a in the z direction and then forwards by d in the x direction, and it doesn't do anything in the y direction. I hope that's clear, right? So to get from Q to P, I don't have to travel in y at all. I just need to go backwards in z by a and then forwards in x by d. So that's how that works. And conventionally you put x first, y second, z third. So I'll just go like this. It's d I hat minus a k hat. That's the full vector that takes me from the charge Q out to the place P. And so the unit vector from Q to P equals the full vector from Q to P divided by the length of the full vector from Q to P. And that's equal to d I hat minus a k hat divided by the square root of a squared plus d squared. Right, I just used the Pythagorean theorem on the bottom. So this thing right here is the square of the hypotenuse length, the dotted line there. So I have to take the square root, and I take the positive square root for the length, of course. So this is the unit vector, and this unit vector is what I need to put right there. So I can finish this. This is 1 over 4 pi epsilon 0, the charge Q, times, it turns out that it's d I hat minus a k hat divided by, so that's a quantity, it's a vector, divided by a square root of a squared plus d squared times an a squared plus d squared.
and I hope you can see this, but this just amounts to raised to the 3/2. So, for example, what if Q was a 2 microcoulomb electric charge? And actually, yeah, so Q is a 2 microcoulomb electric charge. Let's say that A was 1 centimeter. So 1 centimeter is the length A, and D was 2 centimeters. So I already showed you that 1 over 4 pi epsilon naught is roughly equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. Right, that's what 1 over 4 pi epsilon naught is. And you can see that now I have information about 1 over 4 pi epsilon naught. I have the charge Q, here's the number. I have the distance A, 1 centimeter. I have the distance D, 2 centimeters. And when I go and I calculate the electric field of Q at the place P, which is, so the place P in this case is 2, or actually, yeah, at P, let's just call it P, because P is described by A and D and 0 in the Y. You can do this. In fact, right, you'll have to use a calculator. I'm not going to use a calculator for you, but what this is going to give you is the electric field due to Q at P. Whoops. And it's going to give you the x component times I hat plus the y component times j hat plus the z component times k hat. And you can see that when you go and you actually calculate this out, there is no j hat component. So for us, for this problem, there was no component of the electric field in the y. That is, it has value 0. The other two components are newtons per coulomb, because that's, or yeah, if you calculate out for the SI units, you'll have newtons per coulomb. Okay, so that's an example of a point charge. So this finishes, honestly, except for using a calculator. This example, we have the x, y, and z components of the electric field of the charge Q at the location P. So it turns out that if you were to do this work, you can see that the electric field, there is a minus sign in front of the z direction, but there is a positive sign in front of the d direction. So we can actually go over here and do a little bit more summarization. The x component of the electric field is positive. The y component of the electric field we just discovered is 0. And the z component of the electric field is negative. Right? That's what we just got from the electric field. And so the way we would sort of finish this problem is to go in here and actually tack on the electric field. It turns out that the electric field components are going to amount to having an electric field vector that points this way. It points sort of back into the page. It points positively in the x direction. It points negatively in the z, right? It points back into the page. That's the negative in the z. But it does not point up in the y, nor does it point down in the y. It's flat. That is, this arrow lives only in the zx plane. That's the electric field at P. Okay, so yeah, that's the example for a point charge. So let's study the net electric field at place P due to multiple charges, point charges, q sub I. So rough sketch looks like this. Let's have n equals to 4 point charges. So here's 4 point charges. 1, 2, 3, 4. So Q1, Q2, Q3, and Q4. And let's put in a place P. So I'm going to draw the place P in black ink. Put it right here. This is the place P. It's just a mathematical location. All right, so you can see that Q2 is quite close to P. Q1 is a little further away. Q3 is slightly closer. Q4 is far away. Q4, yeah, so these charges each will put electric field at P. So Q2 will put electric field at P. Q1 will put electric field at P. Q3 will put electric field at P, and Q4 will put electric field at P. And the idea is the net electric field at P all it is it is the electric field because of Q1 at P, vector addition with the electric field due to Q2 at P plus the electric field due to Q3 at P plus the electric field due to Q4 at P. And these are all vectors. So earlier, when I showed you this example, can you see that here's the charge Q, and I drew the electric field. This is the electric field due to Q, and you can see that it's at P. I'm drawing it as acting at P or as existing at P. So this is the electric field vector. There is something really important that I didn't end up saying, but I'm going to say really quickly now. So can you see that the unit vector from Q to P is the vector direction that I'm assigning to the electric field? And all of this stuff out front that I'm putting in brackets right now, this has not got any vector quality, but it can carry a plus or a minus sign. So everything in the square bracket is going to be positive if capital Q is positive. And in that case, the electric field is a positive number times that unit vector that points that way, which means that the electric field is parallel. That's in the same direction as the unit vector if the charge is positive. But if the charge is negative, if Q is negative, then the electric field is going to be opposite to the unit vector direction. The unit vector direction will still point away from Q, but a negative charge will take the electric field vector and point it back towards Q. Yeah. So let me move on and use that idea. So let's say that Q1 is positive, Q2 is positive, Q3 is positive. So the electric fields of these charges will just be in the same direction as the unit vector that points to the place P from these charge locations. But for fun, let's do Q4 as negative. It's boring to treat one of these charges as value 0 because then we don't have to include it, of course. Anyhow, so let's go in and draw some vectors. So the electric field, because of Q1 at P, so here is P, here is Q1. Since Q1 is positive, the electric field at P because of Q1 will point away from Q1. So it looks like an arrow that points away from Q1. I'm gonna say that it's this arrow. And the length of it is some number of newtons per coulomb, right? So that's the length of it, is some number of units newtons per coulomb. The electric field due to Q2 at P. So here is Q2. It's a little bit over to the right. It is a little closer to P than Q1 is, so it may have a stronger electric field at P just because 1 over r squared is bigger. The problem is I don't know about the relative size of Q2 versus Q1. If this is a small amount of charge, then it being closer may not make a difference. So because of Q2, all I'm going to sort of roughly keep track of is the direction. It's a little bit steeper downwards, like say this. It's a little bit, it's down but a little bit towards the right. So it's down and a little bit towards the right. This is more like a 45-degree line or something. The electric field from Q3. So here's Q3. The electric field will point up towards the right, like this. And then the electric field due to Q4 at P, this one's the confusing one. So to go from the charge to the point P is this vector, right? But I'm not going to draw this vector here. I'm going to draw the opposite of it. And the reason is because I have to remember that the charge Q4 is negative. So Q1 puts electric field this way, Q2 puts electric field this way, Q3 puts electric field that way, and Q4 doesn't put electric field this way, it puts electric field this way. So these are the 4 arrows that I need to add up according to this rule right here. This rule is called the superposition principle. All right, so roughly speaking, I've got 1 arrow up to the right and 3 arrows down to the right, and so the net force, or I mean the net electric field, equals the first arrow plus the second arrow plus the third arrow plus the fourth arrow, and the net result equals, right, from tip to tail, that's how you add vectors. This is the net electric field at P. So earlier, in the learning outcomes, I described that you really ought to sort of gain a conceptual direction, understanding of how the electric field is going to add up. This is what I mean by it. You sort of imagine the individual contributions and how they combine as vectors. And the combination as vectors is very simple. This is the combination rule, the superposition. Superposition is not laying things over the top. Not, at least not in the sense that we're adding it up. We're adding it up in this vector tip-to-tail style. All right, so I have a particular example. Example with two charges, right? This was an example with 4 charges, and I'd have 4 individual vectors, and I'd have to add up 4 vectors. So instead, I'm going to have an example only with 2 charges, and in particular, I'm going to talk about what's called the electric dipole. And an electric dipole is Q and minus Q separated by a distance, and this is unfortunate, but it doesn't really matter, but it's a distance defined by 2 times some distance a. So I'm going to draw that. So I'm going to draw something that is slightly different from what I drew earlier. I'll describe what I mean in just a second. So here is a coordinate system. Earlier, I drew you, we did a problem where a charge Q was on a z-axis, where the z-axis pointed down and out, sort of towards the left, and a point P on the x-axis. I'm actually going to draw exactly this again, but I'm going to twist the coordinate system around. So the z-axis, I'm going to make it point up. The x-axis and the y-axis point like this. So the x-axis points out of the page down to the left, the y-axis points out of the page down to the right, and the z-axis points sort of out of the page and up, like that. And the way you get to this coordinate system from here is you just imagine taking this coordinate system in the old drawing sense and sort of twisting it, I hope you can see that, and putting it like this. Can you see the z-axis points up now? The x-axis points down and out to the left. The y-axis points down and out to the right. So it gives us a new perspective on the same coordinate system. So this is the I hat, j hat, and k hat directions, and I have a charge Q up top, and down here I have another charge, negative Q, the same distance below the origin. So they'll go down the z-axis like that. So this Q is located at 0, 0, a, and this negative Q is located at 0, 0, minus a. And then the same in this example, out a distance d is the point P on the x-axis. So here is the point P, and it is a distance d out. So the location of P is at d, 0, 0, like that. Okay, so we need, in order to calculate electric fields, so the electric field of point charges, so let's say of the point charge Q, equals, turns out it's Q over 4 pi epsilon 0, 1 over the distance between Q and P squared, times the unit vector that points in the direction of P from Q, looks like this. And so we just need to be able to write down the distance squared and the unit vector, and the charge Q is a given. So the vector RQP, this is the vector that takes me from the charge Q, which is the one up top, out to the point P. And I've showed you how to draw that already. So what it does is it undoes going up a from the origin, so it goes backwards along the z-axis by a, so minus a k hat takes me down to the origin, and then I'll use d times I hat to go out to the place P. So what this means is that the magnitude squared is a squared plus d squared. And it also means that the unit vector from Q to P equals the vector, so it's d I hat. I don't need to add it in z and then x. I can do x then z, so a k hat like this, and then I divide by the distance, right? That's how you construct the unit vector. So I showed you how to do that a couple of different times. So the answer is d squared plus a squared. So it's sort of like a squared plus d squared, except for there's a square root. So I can write down that the electric field due to Q at P equals, so Q over 4 pi epsilon naught. It goes d times I hat minus a times k hat. And then divided by, it turns out it's d squared plus a squared raised to the 3/2 power. If you go through the same kind of stuff with negative q, the electric field, because of the other charge, the negative q, at the same place p though, so same place p, but because of negative q, the charge is negative q. It's not positive q like up there, it's negative q. Divide by 4 pi epsilon 0. This thing is different, so in order to get from negative q to p, I go positively up the z-axis, then positively out the x-axis. So this will look like d I hat plus a k hat. So that's different here. And then I divide by, it's actually the same hypotenuse distance as q is from p to, for minus q to p. So it's just the same thing again. So d squared plus a squared raised to the 3/2 power. Right? So here's my two electric fields. These are electric fields due to individual charges. These are two contributions to field at P. Right? So let's add them up. So the net electric field at P due to both charges, Q and minus Q, is equal to, and it is a vector. So I've got Q over 4 pi epsilon naught. And I hope you can see that actually Q over 4 pi epsilon naught is in both locations. That is, if I remember to move minus over the unit vector, essentially. So I'm going to move that minus sign over the vector. So the first part, and also actually, I forgot, d squared plus a squared raised to the 3/2 power is also common here. So when I add this and this together, I've got kind of a lot of common factors. So 1 over d squared plus a squared raised to the 3/2. So those are all common factors. And then I've got d I hat minus a k hat. So that's those two terms. But these two terms, I have to remember, I'm going to put this minus sign with them. So when I add, right, so plus, this minus sign needs to distribute. So it's minus d I hat minus a k hat, like this. And I'll close the bracket. And what happens, pretty cool, is, check this out. The d I hats, they cancel. So the positive x component to the net electric field and the negative x component to the net electric field, they precisely cancel each other off. And what's left over is negative 2a k hat. So it goes like this. Q. There's a minus. There's a 2 times a. And then I'll divide by d squared plus a squared raised to the 3/2. And then there is the ubiquitous 4 pi epsilon 0. So this, ooh, and I forgot something really important. I don't know if you can see what I forgot, but I had all kinds of I hats and k hats over here, and I forgot to include it so far. So there's the k hat. So in the end, so assumption is, let's say Q was positive. So the positive charge is up here, and the negative charge is there. So at P, so let's draw P. Q is going to give me electric field at P that points away from Q. So it looks like this. That's the electric field due to Q, right? But at P, the electric field due to minus Q does not point away from minus Q. It points towards minus Q. So the electric field due to minus Q does like this. It points backwards. It points backwards towards minus Q. So this would be the electric field because of minus Q. And so you come out and then you go back, which is a net result that is sort of down. So this is the net electric field due to Q and minus Q. And can you see that it points downwards? And down means negative Z. And here it is, negative Z. So the electric field points down. So E net is down.